Let's look at another example. In this example, we want to find the change in entropy when a gas is throttled from a high pressure P1 about 19.66 bar to a low pressure atmospheric pressure at about 1 bar. The initial temperature of this gas is 486.2 Kelvin, and the gas happens to be N-butane. So we have N-butane at some temperature and a high pressure, which is being throttled to a lower pressure. And throttling processes are usually isenthalpic, meaning that there is no change in enthalpy for the process. And what we're interested in calculating is entropy change for such a process. All right? Let's see how we can solve this problem. So for this particular process, let me see if I can sketch a schematic of the steps we can use to calculate the changes in enthalpy and entropy. So initially, I am at a temperature of T1 and P1. So let's call this as A. And my final condition is P2 equal to 1 bar. I do not know the temperature, but what I do know is that it is an ideal gas, right? We're going to break this into a series of steps, right? Going from step A to B, we start with the initial condition and take it to an ideal gas at the same condition. And from B to C, we're going to go from ideal gas at the initial condition to the ideal gas at the final condition. And over each one of these steps, along each one of these steps, we should be able to easily calculate the enthalpy and entropy changes, which is what we are interested in for this particular example. So if you recall, going from A to B, the change is what we call as HR, or the residual enthalpy, right? In fact, it is negative of residual enthalpy because the direction is going from A to B. So this is negative of residual enthalpy at 1, similarly negative entropy at 1. So delta H going from A to B is negative H1R. Delta S A to B is negative S1R, right? This is because delta H A to B is HB minus HA, that is the ideal gas value minus the real gas value, which is by definition negative of the residual thermodynamic property. So if I can calculate the residual thermodynamic property at the initial condition, then I know what S1R are, and hence the change along the path A to B. And from B to C, it's pretty straightforward because all I'm interested in is just the change for an ideal gas going from B to C. And for an ideal gas, if you recall, it's pretty easy to calculate the enthalpy and entropy changes given the specific heat capacity. So let's call this as delta H BC and delta S BC. However, if I have to calculate delta HBC, what I need are the initial and the final temperatures. And the initial temperature, we know it's 486.2 at B, but I do not know the final temperature. T2 is unknown. What I do know is that the final pressure is 1 bar, but then for an ideal gas, pressure doesn't affect the enthalpy. So I still have to figure a way out to calculate the final temperature. And to be able to do that, what we will do is use the information given to us about the process. So let's highlight a few key things here, right? This is an ideal gas-like condition. This is an ideal gas-like condition. And we are also given that the whole process itself is isenthalpic. What that means is that delta H from A to C, which is delta H from A to B, plus delta H from B to C, equals 0. That's because the process is isenthalpic, right? So what this means then is negative of H1R plus delta HB to C is 0. And delta HB to C is the enthalpy change for an ideal gas. So that is, in terms of the specific heat capacities, it is T1 to T2 Cp Ig dt. This equals 0. Now in this, I can use any convenient method to calculate H1R. Similarly, I know the initial temperature T1. I know the ideal gas heat capacities from any handbook, Cpig. So all I do not know in this equation is T2. So because I know everything else, I can use this equation to calculate T2. And once I have T2, I know the initial and final temperatures and pressures, so I should be able to calculate the change in entropy for the ideal gas like condition delta SB to C. And because I know S1R, I should be able to calculate the overall entropy change going from A to C. Let's write that out as well. Delta SB to C is the entropy change for an ideal gas. And if you recall, for an ideal gas, this is given as Cpig by T dt minus R ln P2 over P1. So delta S A to C is delta S A to B plus delta S B to C, which is negative S1 R plus integral T1 to T2 Cpig by T dt minus R ln P2 over P1. Now, if you look at this equation for delta S A to C, I can calculate the residual property at condition 1 using any convenient equation of state or correlations like Lee-Kessler tables, for example. And if I know Cpig and the final temperature, which I will find by solving equation 1 here, right? If I solve equation 1, I will get T2, and if I use that T2 in equation 2, I know the initial and final pressure. So everything in equation 2 can be readily calculated or known, and so I should be able to find delta S A to C. So that's the approach we're going to use to solve this particular problem. So let's start working with each one at a time. The first thing is to be able to calculate the residual enthalpy. And of course, if you're calculating residual enthalpy, let's also attempt to calculate residual entropy, S1R and H1R, right? Let's get some numbers from a suitable reference, a handbook, or the back of your textbook. For N-butane, it turns out that Tc is 425.1 Kelvin and Pc is 37.96 bar, and the eccentric factor omega is 0.2. At these Tc and Pc values, Tr is going to be T over Tc, and from the given temperature, which is 486.2 over Tc is 425.1, I get a Tr of 1.1438. And similarly, Pr is P over Pc, so that's 19.66 bar over 37.96 bar. So that's a Pr of about 0.5179. At these Tr and Pr, N-butane is probably going to be in the vapor phase. You can look at any of the correlations. I used Lee-Kessler tables to find the state of the system. It turns out to be in the vapor phase. And if you recall, the liquid phase is highlighted differently in the Lee-Kessler tables from the vapor phase. So you can look at the Lee-Kessler tables, identify the phase of the system. In this case, it turns out to be in the vapor phase. And I can use these Lee-Kessler tables, do a double linear interpolation for P between 0.4 and 0.6, as well as T between 1.1 and 1.15. And using that double linear interpolation, I will get the value of H naught over RTC and H1 over RTC, S naught over R, and S1 over R at the condition of my interest, which is TR of 1.1438 and PR of 0.5179. And at these conditions, the numbers I get are negative 0.4513, and this is negative 0.2650. And for S, this is negative 0.2758, and this is negative 0.2453. Using these, I can calculate HR. I'm sorry, these need to be HR naught, right? Not H naught. I should have written it as HR naught and HR1, SR naught and SR1. So HR is HR naught plus omega HR1 over RTC, right? And from this I get a HR value of negative 1655.1 joule per mole. And similarly, SR over R is SR naught over R plus omega times SR1 over R. So I get an SR of negative 2.7 joule per mole per Kelvin. So these are the HR and SR values at the initial condition, right? And my initial condition happens to be 1. So these are HR1 and SR1, right? Because all through I have used the condition 1 in these calculations. So now I have HR1 and SR1 values. If you look at this equation 1, I know H1R. What I do not know is the temperature T2. I want to solve this equation to get the temperature T2 like we discussed. So to be able to do that, I need a CPIG value. It turns out for N-butane, CPIG is a function of temperature in this form, A plus BT plus CD squared. This is one of the correlations I have found in the textbook for N-butane, or the ideal gas-like heat capacity for N-butane, the temperature dependency for that. And I'm going to use this, and if I rewrite equation 1, it reads negative of H1R plus integral T1 to T2 CPIG dt equals 0. So what I'm interested in is first writing an expression for CPIG dt, or integral of that value. So from the given relation or temperature dependency, CPIG, or integral of that T1 to T2 dt, will be R times A T2 minus T1 plus B by 2 T2 square minus T1 square plus C by 3 T2 cube minus T1 cube, right? So then equation 1 reads negative 1655.1. That was the value of H1R. H1R was negative 16.51.1, so negative of that will be positive, plus integral T1, which is 486.2 to T2 CPIG dt. Well, let's write the expression we have. R times A T2 minus T1 plus B by 2 T2 squared minus T1 squared plus C by 3 T2 cube minus T1 cube equals 0. From the handbook, the values of A, B, and C can be readily found. For this particular case, A happens to be, of N-butane, A happens to be 1.935, B happens to be 36.915 10 power negative 3, and C happens to be negative 11.402 times 10 power negative 6. And remember, T1 was the initial temperature, which is 486.2. I can make all these substitutions along with the value for R, 8.314 joules per mole per Kelvin. Now everything in equation 1 is known except T2. So I can solve this equation. Any suitable software, you could easily do it in Excel, for example, and it turns out the value of T2 you will get by solving this equation is 474.5 Kelvin. So when you throttle N-butane from high pressure to a lower pressure, the temperature is going to reduce. It's going to reduce by about 11 to 12 Kelvin. Right, this is my final temperature. And we got this by noting that the process is isenthalpic. Now, once I have the final temperature, it's pretty straightforward thereon to calculate the entropy change, delta SAC, from equation 2. All you need is the residual enthalpy at initial condition, and then solve solve that integral for Cp by T dt. Right, we already know the values of, or we already have a temperature dependency for Cp, which I can use in equation 2, just like we did in case of enthalpy, and then we should be able to solve this equation. Now I have T1, T2, Cpig, P1, P2, and the initial residual enthalpy. So let's do that. I'm going to use a different color for enthalpy. So the value or the expression for delta S A to C is negative S1R plus integral T1 to T2 Cpig by T dt minus R ln P2 over P1. This was equation 2. So I'm going to use this equation 2 and to be able to write everything else in that equation. Let's first see what quantities I know. S1R was negative 2.7 joule per mole per Kelvin. R, of course, is 8.314. P2 is 1 bar. P1 is 19.66 bar, right? We have expression for Cp. The ABC values are the same as in case of enthalpy calculation. All we need to do is integrate that expression. So let's first do that integration. Integral of T1 to T2 Cpig by T dt is going to be R times, this is A over T, so A ln T2 over T1 plus B times T2 minus T1 plus C over 2 times T2 squared minus T1 squared. This is the integral value. Again, the ABC values we already know. I know T1, I know T2. T1 is 486.2. T2, we just got it as 474.5. So I substitute everything in this equation to get delta SAC. And the value I obtain is 24.02 joules per mole per Kelvin. This is value of delta S going from A to C. So what we have done in this problem is considered a process wherein a real gas undergoes a certain change. We know some information about the process, and then we try to calculate the other thermodynamic variables, including the temperature in this particular example. So this is how we're going to use whatever we have learned so far to be able to perform a calculation over the process. So let's quickly then summarize how we went about calculating property changes for pure species. Let's quickly recap what we have done so far in terms of calculating property changes for a variety of cases. We have used ideal gas expressions. That's the simplest way to calculate the property changes if, of course, such a condition is applicable. Otherwise, we have to resort to equations that are applicable for real gases, and the way we have handled real gases is using residual properties. We'll come back in a minute and talk about how to calculate residual properties for various cases. And then we had developed some equations for liquids in terms of isothermal compressibility and volume expansivity. Talking about various conditions at which several types of expressions we have used so far are applicable. The ideal gas-like conditions are applicable at low densities when the molecules are far apart at large molar volumes, right? Which typically is the case either at low pressure or high temperature. If we want to correct for non-ideality, or we want to use equations for real gases, then the easiest way we can approach that is using a virial equation of state with just the second virial coefficient. But then it's applicable from low to moderate pressures, right? If the pressures are slightly higher, maybe if we have enough information, then we can use the third virial coefficient. Otherwise, we usually resort to cubic equations of state that are appropriate for that particular species we are using. In some cases, Redlich-Kwong might be more suitable. In some other cases, Peng-Robinson might be more suitable, or some other cubic equation of state, right? It depends on the species we are using. Similar to cubic equations of state, if we use theorem of corresponding states, then we use either via the Pitzer correlations. The most popular ones are Lee-Kessler tables. In fact, Lee-Kessler tables, in addition to the compressibility factors from which we can calculate the molar volumes, we have Lee-Kessler tables also for residual enthalpies and residual entropies. As far as liquids are concerned, we can calculate the saturated liquid volume using Racket equation. We can assume that liquids are fairly incompressible at normal temperatures and pressure changes. They're fairly incompressible, or their molar volume change is 0. But if there is a large change in pressure, but then if they are not incompressible, then we can make an assumption that the volume expansivity and isothermal compressibility are fairly constant, which is the easiest way to handle the changes in temperature and pressure to be able to calculate the corresponding volume change for a liquid. If that is not applicable, then of course we need the temperature and pressure dependency for beta and kappa to be able to calculate the change in volume. One of the other methods we looked at for calculating molar volume of a liquid is using what we called as Linderson correlation. And to be able to use this correlation, we need molar volume at a certain condition, and we can use the two-parameter theorem of corresponding states to be able to calculate the molar volume at a different condition. So this is a quick summary of what we have done so far, and if you look at it, in most cases it is limited only to pure species. When we come back in the next lecture, what we'll do is try to extend these ideas for mixtures of liquids or gases.